Hello, this is our Math 1050 review for Chapter 1. Our goal here is to work through some problems and review some of the main concepts of Chapter 1. And let's go ahead and get started. Okay, first of all, we have y equals 2, which is the constant function. And what we're going to do is begin with the toolkit functions. Just look through these toolkit functions and make sure that you're good with graphing, with knowing what the names of these functions are, and with knowing some properties of these functions. Y equals 2 is what you usually see the constant function, y equals c. Well, in this case, we're letting c be 2 for our particular graph here. This is a graph of y equals 2. The domain of this function is all real numbers. As you can see, all x values are included on our graph here. The range is there's only one value in the range, and that would be y equals 2. And so we can write the range in interval notation as square bracket 2 comma 2 square bracket. This means that we're including the number 2, but nothing else in our range. And another thing that we want to look at is symmetry. Well, if you think of this graph being reflected about the y-axis, the graph would be itself. And so we can say that this graph is symmetric about the y-axis, which tells us that the function is even. The graph of any even function is going to be symmetric about the y-axis. Okay, moving on. Y equals x is the identity function. To graph this function, we sketch a line that basically splits the first and the third quadrants in two. The domain of the identity function includes all values of x, so we would write this in interval notation as negative infinity to infinity. The range also is all y values, so would be negative infinity to infinity. This graph is symmetric about the origin. If you think of rotating this graph through an angle of 180 degrees, you would have the same graph. And so we say this graph is symmetric about the origin, which tells us in terms of even or odd, a graph of a function that is symmetric about the origin, this would be an odd function. Moving on to y equals absolute value of x. The absolute value function looks similar to y equals x, except that the part of the graph in the third quadrant moves up to positive values in the second quadrant. The domain of this absolute value function includes all x values. Negative infinity to infinity would be our interval notation for this function. The range actually starts at y equals 0, and past that includes only positive values of y. So our range is square bracket 0 to infinity in interval notation. The symmetry, again, is about the y-axis, like the first function we looked at here. As far as even or odd, being symmetric about the y-axis tells us that the function is even. We move on to y equals x squared. This is what we refer to as the quadratic function. The graph, there's usually 5 main points I would plot to give me this graph. 0, 0, 1, 1, 2, 4, negative 1, 1, and negative 2, 4, about right here. Okay, so the quadratic function looks like so. We'll use this function a lot in Math 1050. The domain here includes all x values. If we could continue this graph on forever, we would be able to actually grab all x values, so negative infinity to infinity. Like the absolute value function, the range starts at y equals 0 and then continues on to take on all positive values for y. The symmetry about the y-axis, similar to the absolute value function. Is it even or odd? Being symmetric about the y-axis tells us that the function is even. Y equals x cubed. This is the cubic function. Looks like so. For this function, if I was graphing it by points, I would probably plot 0, 0, 1, 1, negative 1, negative 1, 2, 8, which isn't quite on this graph, and -2, -8. The cubic function has a domain of all real numbers. The range is also all real numbers. The symmetry, in this case, if we rotate 180 degrees, we'd have the same graph. And so the symmetry is about the origin, telling us that the graph is the graph of an odd function. Y equals 1 over x. This graph is a little bit different. This is the reciprocal function. And the graph actually takes on two different parts for this function. If I was plotting this using points, I would plot 1, 1, -1, -1, 2, 1/2, 1/2, 2, -1/2, -2, -2, -1/2. And from there, I would remember that anytime x is 0 here, the function will not be defined. From there, I would look at the domain of the function, which, because x equals 0 is not defined, we go from -infinity to 0, not including 0, and then 0 to infinity. The range is similar. The y values on this graph also leave out the value of 0. There's no y equals 0 on our graph here. So the range is -infinity to 0, union 0 to infinity. Is this graph the graph of an even or odd function? Well, if you look at the symmetry, rotating 180 degrees would give us the same graph. So the graph is symmetric about the origin, telling us that we have an odd function here. Similar to the reciprocal function is the reciprocal squared function. Instead of y equals 1 over x, we have y equals 1 over x squared. The x squared changes the behavior of this graph a bit. So we have the graph in quadrants 1 and 2 telling us that the domain would exclude 0 again, because if we threw 0 in here, we'd have a 0 in the denominator. So our domain is going to go from -infinity to 0, union 0 to infinity. The range, however, is unlike 1 over x. The range starts above the x-axis, so it doesn't include 0, but it does include all positive values for y, so the range would be from 0 to infinity. The symmetry, if you can look at the graph, is about the y-axis, again making this graph an even, making this graph the graph of an even function. Okay, so moving on, y equals square root of x, one of my favorite functions. This is the square root function. Looks like so. Plotting points on this, I would plot 0, 0, 1, 1, 4, 2. And the domain of this function, this is a little bit different than any of the other functions. It's only in quadrant 1, but the graph does start at 0, 0. So we would include x equals 0 in our domain. We'd have 0 to infinity. The range is going to be the same. The y values start at 0 and go to positive infinity. And the symmetry, since the graph only exists in quadrant 1, there's actually no symmetry, and the graph is neither even nor odd. Or the function that the graph represents is neither even nor odd, I should say. Okay, cube root of x. This is the cube root function. Graphing by plotting the opposite points as you would for the cubic function. We would have 0, 0, 1, 1, -1, -1. We'd have 8, 2 out here somewhere, and -8, -2 out here somewhere for the cube root function. The domain includes all x values. The range includes all y values. The symmetry, rotating 180 degrees, gives us the same graph. So our graph is symmetric about the origin, telling us that the function is odd. Okay, moving on. We're going to look at some examples here and determine which of these relations represent functions. The first relation that we have here is a set of ordered pairs. And if we remember, the definition of a function is a relation in which any two ordered pairs with the same first component also have the same second component. So here we have a violation of that definition because we have a first coordinate of 1 associated with -3. We have another ordered pair that has a first coordinate of 1 associated with -4. So we would have to say this function does not represent, or this relation does not represent a function. So I'll just say no, this relation does not represent a function. What about this second relation where we have 1, the ordered pairs 1, -3, 5, 2, -1, -4, 3, 2. Notice that each ordered pair here has a different first component, so there's no way that we would have the same first component corresponding with two different second components. So without even going any further, I can say yes. All right, let's move on to a graph. How do we tell if a graph represents a function? Well, we use the vertical line test. For the vertical line test, a graph represents a function if no vertical line intersects the graph at more than one point. Well, we can see we could draw a vertical line here. In fact, we could draw a lot of different vertical lines that would intersect the graph at more than one point. So this graph is not a function. It's not the graph of a function. What about this? Oh, this is kind of a crazy graph, but does this graph represent a function? Well, any vertical line we draw here is only going to cross through the graph one time. So we would have to say, yes, this is a function. Okay, moving on. We have a square root function here where we want to find the domain. We have f of x equals the square root of 2 minus 5x. Anytime I see a square root, the first thing I'm going to do is remember, if I'm looking at the square root of x, that tells me that x has to be greater than or equal to 0. If something else is under that square root sign, whatever is under that square root sign, in this case 2 minus 5x, is going to have to be greater than or equal to 0. Just by writing down this first step is a good way to get the right answer here. And then I'm trying to get x by itself. So the first thing I would do here is subtract 2 from each side, giving me -5x is greater than or equal to -2, and then dividing through by -5. So when we divide through by -5, -5 is a negative number, so we're going to have to flip this inequality sign when we divide through by a negative number. What we're going to end up with is x is less than or equal to 2/5. Okay, so we almost have the answer. The thing I would like to do, well, I'd say this is the answer. X has to be less than or equal to 2/5, but I would like to see this in interval notation, which would be -∞ to 2/5 with a square bracket. All right, and it's a good idea to circle your final answer, so we'll do that here, and we'll move on. We have another function here, g of x equals x minus 3 over x squared minus 9. For a rational function, we want to make sure that the denominator is not equal to 0. In this case, this function can be factored to make it x minus 3 over x minus 3 times x plus 3. But we don't change the function before we look for that domain. We just look at whatever is in the denominator. Because I'm sure some of you are seeing we could simplify. We cannot simplify when we're finding the domain. We have to make sure that each factor in the denominator is not equal to 0. And so I'm going to make sure that x plus 3 is not equal to 0. X minus 3 is not equal to 0. That means that x cannot be equal to -3, and x cannot be equal to, whoops, this should be x cannot be equal to +3, and x cannot be equal to -3. Okay, so we basically know what's in the domain, all real numbers except 3 and -3. To write this domain in interval notation, we would start at -∞, go up to -3, put a curved bracket there, union, curved bracket, -3 to 3, and we leave out 3, so we put a curved bracket again, union 3 to infinity. Okay, so this is our domain for this rational function. The next problem that we're looking at here is we have f of x equals 3x plus 1 over 4 minus x squared. And there's not really a problem here, but there will be now. So what we want to do here is we want to find f of 0. To find f of 0, all we do is plug in 0 wherever there's an x. So we have 3 times 0 plus 1 over 4 minus 0 squared. That would give us 1 over 4. So f of 0 is 1/4. What is, graph-wise, if we graph this function, what have you found? So when you found f of 0 equals 1/4, setting x equal to 0 actually gives us the y-intercept. So what we found is the y-intercept. And the y-intercept as a point on the graph would be the point 0, 1/4. So this would be a point on the graph. Okay, moving on. This is a little bit different problem, same function, but this time we're going to solve f of x equals 0. That means I want to set f of x equal to 0 and figure out what values of x would make this happen. So we have 0 equals 3x plus 1 or over 4 minus x squared. Well, the only way that a fraction can equal 0, if you think about it, is if the numerator equals 0. In this case, that would mean that 3x plus 1 would equal 0. And we would subtract 1 from each side, giving us x equals negative 1/3 when we divide through by 3. Okay, so we've solved f of x equals 0, and what have we found here? Well, here what we're doing when we set f of x equal to 0, we're setting y equal to 0. So here we're finding the x-intercept. The x-intercept for this graph would be the point negative 1/3, 0. All right. Now the piecewise defined function. These you have probably seen in a previous algebra class, but I'm going to try to use a different technique that will help you a little bit with graphing these. These tend to be a problem. The first thing I'm going to do is I'm going to look at y equals x squared. So we looked at y equals x squared earlier. In fact, I just copied that graph here. That's why we are very interested in these parent functions, also called the toolkit functions, because these show up a lot. In fact, right here, if we're graphing this piecewise defined function, the first part of this piecewise defined function is going to be f of x equals x squared, or y equals x squared. So here, if we were graphing y equals x squared, we'd include the whole graph, but we're only interested in part of this graph for our final piecewise defined graph. And the part of the graph that we want here is from where x is less than or equal to negative 1. So I'm going to look at my graph of y equals x squared, and because we have an equal sign here, we're going to include the point where x equals negative 1 right here. And then if x is less than negative 1, we're also going to include the points to the left of that. So we're going to include the part of the graph y equals x squared at x equals negative 1 and any points on our graph that are to the left of x equals negative 1. I'm going to go ahead and move that part of the graph over here. So we'd have x equals negative 1. If you remember some important points on the graph of y equals x squared, negative 2, 4 would be on this graph. So just to make this a little bit cleaner graph, we'll throw that point on there, and then our graph would kind of curve up something like that. It's hard for me to sketch graphs on the way that my computer is set up here, so this should actually have more of a curve right here, but I don't know if I can do any better. So okay, so anyway, it should be a curve. Now let's move on to the second part of this graph. In the second part of the graph, we're going to be graphing. Let me change colors here too. That might help a little bit. So next we're going to be graphing f of x equals x plus 2. So if I went to graph y equals x plus 2, it would look like so. It would basically be the graph y equals x, but it would be moved up by 2 units to give us a y-intercept of y equals 2. And so this is the graph of y equals x plus 2. We're going to take part of this graph and we're going to move it over to our graph that we're going to finalize for this piecewise defined function. The part of this graph we want is -1 less than x less than 1. That means we're not going to include -1 and we're not going to include 1, but we are going to include all values between those. At x equals -1 on this graph, I'll put a hole here. At x equals 1 on this graph, I'll put a hole. And so we're not including those two n values, but we are including everything between those two n values. Okay, so I'm going to take this part of the graph, y equals x plus 2, and move it over to our main graph here, where we would put a hole at the point -1, 1. But look, this point's already filled in, so we don't need to put a hole there because there's already an existing point. And then we would go up to the point 1, 3, and we would put a hole. Okay, and then try to connect with a straight line here. Okay, well, that looks a little bit better than my first y equals x squared, maybe. That's really bothering me, but, well, let me try to fix it. It may not look any better, but we'll try. In fact, it could look worse. Oh, that's a little bit better. That looks a little more curvy, huh? Okay, so let's move on then. We're not quite finished here, and let me change colors once more. Oh, let's see, what should we do? Well, let's use red, I guess. So the third graph that we're doing is f of x equals square root of x. And I have that one ready to go as well. So here is y equals square root of x. The part of this graph we want starts at 1, includes 1, because the equal sign is included there. So I'm going to plot the point. I'm going to put a dot at the point 1, 1 here. And then we're going to include the point on this graph where x equals 4, because we have an equal sign here. So we have 4. This would be the point 4, 2 on this graph. And then we want all points -1 is less than or equal to x is less than or equal to 4. So we want all points between 1 and 4. And I will go ahead and move this part of the graph over to the final graph that we're working on, starting at the point 1, 1, going up to the point 1, 2, 3, 4, 4, 2 right here. And this has a bit of a curve as well. Okay, something like so. So anyway, this is our final graph. This is what the piecewise defined function would graph as here. Okay, we'll go on to our next problem, which is to classify a function as even, odd, or neither. So here you need to remember that when a function is even, that tells us that f of x equals f of negative x. When a function is odd, negative f of x equals f of negative x. Okay, so the first thing I'm going to do is find f of negative x, which I would do by anywhere I have an x, I will replace that with negative x. So we have 3 times negative x plus 5. 3 times negative x is negative 3x. We have negative 3x plus 5. And I'm going to take a look now. So here is f of negative x. Here is f of x. These functions are not the same. So f of negative x is not equal to f of x. And that tells me that this function is not even. I'll move on to find negative f of x, which I can do by putting a negative out in front of the entire function in brackets. This reminds me that I need to take the negative of each term here. And so negative f of x, distributing that negative through, would be negative 3x minus 5. Okay, I'm going to square this in here. And I'm going to look back. Does negative f of x equal f of negative x? These aren't the same, are they? Because f of negative x is negative 3x plus 5. Negative f of x is negative 3x minus 5. So we also can see that negative f of x is not equal to f of negative x. So this function is not odd, from which we can conclude that neither is the solution here. The function is neither even nor odd. All right, and moving on, I think I have one more of these. To classify the function is even, odd, or neither, we have g of x equals 2x squared minus 1. So g of negative x is the first thing we would look for. We would find that by substituting negative x in parentheses for the x. So we have 2 times negative x squared minus 1. Well, negative x squared is the same as x squared. So keep that in mind. Negative x squared is the same as x squared. So I'm just going to replace 2 times negative x squared with 2 times x squared. And then we have minus 1. Well, in this case, if you look at g of x and you look at g of negative x, you can see that these are the same functions. G of x equals g of negative x. And so we can see right now that our function is even. It's not a bad idea to go ahead and find negative g of x. Just to confirm, negative g of x here, we would find by putting a negative in front of brackets holding our entire function. G of x is 2x squared minus 1. Distributing that negative through would give us negative 2x squared plus 1. And we can see this is negative g of x. We can see that negative g of x is not equal to g of negative x. All right, so we can move on. This function, this crazy function, we have a bunch of stuff going on here. The domain, to find the domain, we look for all the x values included on the graph. And we did this with Toolkit Functions, but the way you can think of this, if I smash my graph down onto the x-axis, so if smashing my graph to the x-axis, notice to the left we head off towards negative infinity. Our domain would include all x values headed out toward all negative x values and all positive x values until we get up to x equals 1, 2, 3, 4, 5, 6. Okay, so to write the domain, we'd write that as negative infinity to 6 square bracket, or we could also say x is less than or equal to 6. The range is the y values, so to find the y values, we would think of smashing our graph onto the y-axis. And let's see what would be the smallest y value. Well, notice we're headed on down in the y direction towards negative infinity as well. And so the range would start at a y value. Well, it's not a y value. It's the smallest possible negative y value we could find. So we're going to write this in interval notation as negative infinity to the largest y value would be right here at 1, 2, 3 at x equals, or at y equals 3. So negative infinity to 3, including 3. Where is this graph increasing? Well, let me erase some of this junk I put on here. Let's erase anything that we're not going to need to use here for where the graph is increasing. I'll leave the numbers on there because those could come in handy. So the graph is increasing if we go from left to right, and we're thinking of where we're walking uphill. The graph starts increasing from its very beginning, which we can't see, so it increases until we get up to here at this top point where x equals -2. We list the intervals of increase with the x values. So starting at x equals negative infinity, or starting at negative infinity to -2, the graph is increasing. Okay, where else is the graph increasing? Well, here we're going downhill from -2 to 3, but then starting at x equals 3, we would, going left to right, we start walking uphill again until we get to x equals 5. So from 3 to 5, we're increasing, and that's about it, right? Okay, so where is the graph decreasing? So where I'm looking at walking downhill, I'm starting at x equals -2 and walking downhill until I get to x equals 3. So from -2 to 3, and then anywhere else, it looks like from 5 to 6, going left to right, we're walking downhill. So also from 5 to 6. Okay, moving on, we're going to look at this same graph to find local maxima and local minima, absolute maximum and absolute minimum. Some of these may not exist, but we'll go through and see. So a local maxima you can think of as standing on a mountaintop, like right here. If I'm standing on a mountaintop and I can see to both sides of me, then I'm going to be at a local maxima. So our local maxima is a y value. This y value here would be y equals 3. So we could say the local maxima is y equals 3. We also sometimes like to make a note of what point that occurs at. So the y equals 3 is going to be at the point, what is that, -2, 3. Do we have any other local maxima? Well, it looks like right here. We're standing on a mountaintop looking off to both sides. And so at this local maxima, we would be at the point 1, 2, 3, 4, 5, 5, 2. So our local maxima at this point is y equals 2. And that y equals 2 occurs at the point 5, 2. Does this graph have any local minima? It looks like there's only one right here. So here we're in a valley and we can see up both sides to looking up towards the mountains from the valley, I guess you would think. And so this is at the point 3, -2. So our local minima here, our local minimum is y equals -2. It occurs at the point 3, -2. All right, and you might think that right here we have a local minimum, but we don't, because you can't see up on both sides from the valley. So you have to be able to see up to both sides, to the left and to the right, to be at a local minimum. Is there an absolute maximum here? This is easy. It's just the highest point on the graph. So yeah, right here we have a local maximum. We have an absolute maximum. Our absolute maximum is y equals 3. Is there an absolute minimum? If you notice, our graph keeps shooting on downwards, and so there's actually no smallest point on our graph. So in this case, we would say no, there's no absolute minimum here. All right, let's look at the next problem that we have. Find a formula for a function g whose graph is obtained from f of x equals 1 over x after the sequence of transformations. The first thing we want to do is we want to take 1 over x and we want to reflect across the x-axis. To reflect across the x-axis, all we're going to do is we're going to write our transform function as y. We're going to throw a big negative out in front of 1 over x. And this reflects our graph about the x-axis. The next thing we want to do is we want to shift right by 3 units. So to shift right by 3 units, we'll have a new function. We have -1 over x, but we need to do something. So shifting left or right affects the input value of x. And it does the opposite of what you'd think. So shifting right, I think of right as plus, but remember, shifting right or left, we do the opposite. So I'm going to have 1 over x minus 3 here. Okay, and then we move down to shift down by 2 units. Well, this is easy. All we do is we write this as y equals -1 over x minus 3. And out here to the right, we're going to just put down 2 units, minus 2, like so. So this would be our y equals, and we're actually asked to call this g, so I guess I'd say g of x equals -1 over x minus 3 minus 2, and this is our required function. And notice that we're going from one step to the next. We're not starting fresh at each of these second and third steps. A similar problem is, this is the same things we did before, but in a different order. So I want you to pay attention to the order here. We have the same function, f of x equals 1 over x. This time we start by shifting down 2 units. So we'll have y equals 1 over x minus 2. And then we shift right by 3 units, similar to what we did before. We change 1 over x to 1 over x minus 3. We still have the minus 2. What really changes here, and this is a mistake often made that I've noticed, is reflecting about the x-axis. Where before, when we reflected about the x-axis, we just put a negative out in front of the 1 over x. Here we need to put a negative out in front of the entire function from the previous step. So I'm going to have the negative of 1 over x minus 3 minus 2. And that results in our g of x function here being equal to negative 1 over x minus 3 plus 2. Okay, so the order of these functions is really important. Now we're going to graph a function from a given function. Well, it doesn't say that this function we're looking at here is f of x. This is y equals f of x. It should state that on the graph. And what we're going to do with this function, y equals f of x, is from this, we're going to graph a transformation of the function, y equals 1/2 f of negative x minus 3. And I'm going to maybe make a bit of a mess of things, but I'm going to use this graph that we're shown here, and I'm going to put some other graphs kind of on top of it. So let's start with, and the order I would go in, I would start inside here. This is the input to the function f. I would start by making those changes first and transforming a function. We've only got one here. We're taking f of negative x. So f of negative x, rather than reflecting across the x-axis like we did in the previous problem, we're going to reflect across the y-axis. Okay, and you can think of that changes that you make to the input to a function reflect or cause the function to change horizontally. So this function is going to change horizontally, reflecting about the y-axis. Well, actually, if we start to the left here, if I reflect this point negative 2, 0 about the y-axis, I'm to the point 2, 0. If I reflect the point 0, 4 about the y-axis, well, I'm still on the y-axis. So we start by moving this first line to right here. This first line segment just goes right here. The second line segment from 0, 4 to 2, 0. Well, 2, 0 reflecting about the y-axis would come over here. And so the line segment that originally was from 0, 4 to 2, 0 now is going to go from 0, 4 to negative 2, 0. And we have one more point to reflect across the y-axis. This is the point 4, negative 2. Reflected about the y-axis would bring it over to negative 4, negative 2, right here. And this point is connected to our reflected point, negative 2, 0. Okay, so this now is negative 4, negative 2. Okay, hopefully that makes sense. It might have been simpler to go on a different graph or use a different color, but anyway, the next thing we do then is I move slowly away from this input value to my function. So the next thing I'm going to do, and I'll do this in red so it's a little easier to see, the next thing is this 1/2. What does this 1/2 do to my function? Well, what this 1/2 do is it's going to vertically, if it was 2, we would say it vertically stretches the graph, but I guess we could say it vertically, well, we can say it vertically stretches by a factor of 1/2. So we'll say it vertically stretches, but really we're not stretching here. We're compressing, I guess you would say. So what 1/2 does is anytime I have a point on my graph, like negative 4, negative 2, we're going to multiply that y value by 1/2. So the point negative 4, negative 2 would become negative 4, negative 1. the point negative 2, 0, multiplying 0 by 1/2 would still be 0. So we're going to go from negative 4, negative 1 to negative 2, 0. The point 0, 4, multiplying the y value of 4 by 1/2 takes me to the point 0, 2. And I'll connect the point negative 2, 0 with the point 0, 2. And now we move on to the point 2, 0. Again, multiplying 0 by 1/2 is still 0. So we go from 0, 2 to 2, 0. And we've taken care of the vertical stretch here. The last thing we have to do, and as I put in this last step, I'll move my graph over to the final graphing plot. The final step here is this -3, the vertical shift. And the vertical shift I would always save for last. So this is going to move the graph in which direction? -3 moves it down by 3 units. Okay, so I'll take each of my points in red over here. So negative 4, negative 1 is going to go down 3 units. So 2, 3, this would be negative 4, negative 1, 1, 2, down 3 units till we're at the final point of, what would this be? Negative 4, negative 4. Okay, so we've taken care of this point. The point negative 2, 0 would move down 3 units. So negative 2, 0 moves down 3 to right here to the point negative 2, negative 3. Okay, so we have our first part of the graph. The point 0, 2 moves down 3 units to 0, negative 1. And we'll connect the point negative 2, negative 3 with 0, negative 1. It should be a little bit straighter line segment than what I've drawn, but that's probably good enough. And then we take the point 2, 0, and we're going to move this point down 3 units to become the point 2, negative 3. Okay, so we'll connect 0, negative 1 with 2, negative 3. And this is what your final graph should look like here. All right, moving on. This is from the textbook, and if you need a guide to graphing these functions or to transforming the functions, I would pretty much just do what we've been doing up till now, but there's a couple steps in here that are really helpful. And if you can think of your function in the form y equals a times f of bx minus c plus d, the first 2 steps here really help you with the next function that we're going to look at in particular. So whatever you end up with c, if the very first step you do is to add c to each x coordinate, that's going to result in what you need to do if you have, particularly if you have a b and a c where the b is not 1 and the c is not 0. If you start with adding c to each x coordinate, and then secondly you figure out what b is, and then you multiply the x coordinates by 1 over b, it's going to give you what you need as a final result there. And so we're going to practice this with the next problem that we have. The next problem that we're looking at here is to graph y equals the square root of 2x minus 4, which I actually consider to be maybe the toughest thing that we do here, just because you have 2 different horizontal things going on here. You have the square root of 2 times x minus 4, all under the square root sign. So what we're going to do is I'm going to think of this function as being y equals the square root of, well, let me actually backtrack that a sec. Let's think of this as being y equals f of bx minus c, which in this case would be the square root of bx minus c. So from this, you could see hopefully that in this case b would be equal to 2 and that c would be equal to 4. Okay, so if we notice this, and the first thing that we do here is, if we go back to the previous note here, the first thing we do is we add c to each of the x coordinates on our graph. Well, what graph are we starting with here? Actually, we're going to start with a graph of y equals square root x. And I'll put on my three favorite points here, 0, 0, 1, 1, and 4, 2. Okay, so if I put on these 3 points and plot the graph of y equals square root of x, the first thing we're going to do, go back again, add c to each x coordinate. So here's c. We're going to add c to each x coordinate. So if we do that, I think I'll try to sketch this kind of off to the side here. Let's see if we can do that. It's going to make a longer graph along the x-axis here. So along the x-axis, we would starting with 0, 0, we're going to add c to the x-coordinate of 0 here. That's going to give us a point 4, 0. So 1, 2, 3, 4. We have the point 4, 0. And then for the point 1, 1, if we add 4 to the x-coordinate of 1, we would have the point 5, 1. And then finally, the point 4, 2, adding 4 to the x-coordinate of 4 here, we would end up with 8, 2. So we're at 5, 6, 7, 8. This would be 8. And our point here is going to be 8, 2. All right, so here we go. So we have, we've taken care of the c equals 4. And I think I'll change colors here before we move on to taking care of b equals 2. So what does b equals 2 do? Well, what we do with b is we multiply each of the x coordinates by 1 over b. So what we're looking at this first transformation of the graph. So we're going to take each x coordinate. Let's start with a point 4, 0. So if I so what is 1 over b? In this case, 1 over b is 1/2. So we're going to multiply each x coordinate here by 1/2. That we'll take the point 4, 0 and move it to the point 2, 0. So we're right here at 2, 0 for our first point. It will take the point 5, 1. We'll multiply the 5 by 1/2. So we would have 5 halves. 5 halves is the same as 2 1/2, so we'd have 2 1/2, 1, about right here. And then we take the point 8, 2, and we multiply the 8 by 1/2, so we would have then the point 4, 2, 1, 2, 3, 4, 1, 2, about right here. And this would be our graph of y equals the square root of 2x minus 4. If you want to kind of check that you've done this correctly, a check would be, let's look at our function y equals the square root of 2x minus 4. What happens if I plug in 2 here? So if x equals 2, if x equals 2, we would have y equals the square root of 2 times 2 minus 4. That would give us 0. That works. We have the point 2, 0, and that checks. That does work. What about here? Well, let's just plug in x equals 4 here. And we can see what we should end up with. If x equals 4, we have y equals the square root of 2 times 4 minus 4. We get the square root of 8 minus 4, which is the square root of 4, or 2. So we have the point 4, 2. That works. Okay, so we got it. Next, we move on to composition of functions. I have f of x equals 3x minus 1 and g of x equals 1 over x plus 3. I want to find g composed with f of x. So g composed with f of x, the way I work these out is I start by, sometimes in math, if you write in steps, it actually ends up saving time, which I find with this type of problem it does. I write g composed with f of x as g of f of x. And then I write g of f of x as g of 3x minus 1. This makes it a little more clear what you're doing. Now you're taking 3x minus 1 and you're plugging it in for the x's in g of x. So I'm going to have 1 over, I replace the x with 3x minus 1, and then we have plus 3. And that results in simplifying 1 over 3x minus 1 plus 3 would be 1 over 3x plus 2. All right, so that's our g composed with f of x here, 1 over 3x plus 2. Our next problem is to, I think these are different functions. Yeah, we want to, here we have f of x equals the square root of 3 minus x, and g of x equals x squared plus 1. I want to find f composed with f of 2. So we have a number instead of x that we're inputting here. And again, I'll start by writing f composed with f of 2 equals f of 2 equals f of, and then to find f of 2, I look at what f of x is, and I'm going to replace that x with 2. So I'm going to have the square root of 3 minus 2 here. So now I have f of the square root of 1, which is 1. Okay, now I'm going back to f of x again, but this time I'm plugging in 1 for x. Okay, so I'm going to have the square root of 3 minus 1. We end up then with a final answer, the square root of 2. Okay, the next problem is to find the domain of f composed with g of x, where we have f of x equals 3 minus x squared, and g of x equals the square root of x plus 1. This is one of the harder things to do, to find the domain. But if I think of this, f composed with g of x, if I start by writing this as f of g of x, then the first thing I look for is I look for this inner function. The inner function here, which you can see is inside, the inner function is g of x. I look totally at g of x, and I want to find the domain of that inner function. The domain of this inner function here, well, this is a square root function, so I would start by saying x plus 1 is greater than or equal to 0, which tells me that x is greater than or equal to negative 1. This is going to have to exclude values that are less than negative 1 for our final domain of f composed with g. The other thing we look at is if I think of f of g of x, well, what am I doing to g of x? When I put g of x into f of x, I'm going to have 3 minus g of x squared. Is there any value for g of x that I could not put in here? Well, actually, there's no number that I would end up with that I couldn't square, right? We're just throwing g of x into a polynomial. So the domain here, if you would think of it for the outer function, there's no more restrictions because we're putting g of x into a function where g can be any number. Let me just off to the side. I kind of hate putting things off to the side because sometimes that gets to be confusing. But if I had another problem where, say, f of x was 1 over x, then f of g of x would be 1 over g of x, and I'd have to be careful that g of x was not equal to 0. Okay, so I would have to also make sure that the square root of, in this case, it would be, it's not letting me write, the square root of x plus 1. I need to undo what I just did there, I think. Oh, now it's going to text. Okay, so somehow this messed up. Although it would not hurt, I guess, to have closed captioning. So that's what we're actually doing now. We're closed captioning this. Okay, so this tells us that the square root of x plus 1 is not equal to 0. Okay, actually, that got rid of it. Okay, it would be good to have closed captioning on this, so I should probably try that with some other videos that I make. So the square root of x plus 1 is not equal to 0. Basically, that's going to tell us that x could not be equal to -1 here. So we would have to exclude the -1. This is a made-up problem, so it's not part of this. Okay, but I'm going to go back to the problem I was working on. So there's no restrictions on we think of this as the outer function. The outer function does not impose any more restrictions on the domain of f composed with g of x. The inner function does compose the restriction that x has to be greater than or equal to -1. This is our only restriction here. So our final answer for this one, the domain of f composed with g of x, would be x has to be greater than or equal to -1. In interval notation, that would be -1 to infinity. All right, let's move on. This is a very popular type of problem. We want to find, for f of x equals x squared minus 2x, we want to find f of x plus h minus f of x over h. And so to do that, the first thing I'm going to do is draw a fraction bar here. I'm going to keep the h in the denominator. It's important to keep that h there, even though I know it takes more writing. It's important to keep that there for the entire problem. And I'm going to start by color coding this a bit. I'm going to start by color coding f of x plus h. So f of x plus h, looking at what f of x is, for f of x, to write down what f of x plus h is, wherever I have an x, I'm going to replace that x with x plus h in parentheses. So instead of x squared minus 2x, I'm going to have x plus h squared minus 2 times x plus h. Okay, and then we have minus f of x. So we have minus, and for the f of x, let's make that green. And so f of x is just what we're seeing here. What f of x is x squared minus 2x. Okay, so now I move on to expanding. And sometimes this next step takes a huge fraction bar, so we'll do that. To expand x plus h squared, think of this as x plus h times x plus h. If we FOIL x plus h times x plus h, we have x squared plus xh plus hx, which would give me plus 2xh, and then plus h squared. Okay, so I'm going to replace x plus h squared with x squared plus 2xh plus h squared. I'm going to distribute the -2 through to the x plus h so that we have minus 2x minus 2h, and then I'm going to be very careful to distribute this negative through to both the x squared and the -2x, so that we end up here with minus x squared plus 2x all over h. Okay, at this point, we should be able to cross out some stuff. X squared minus x squared adds to 0, so we can cross out x squared minus x squared. -2x plus 2x adds to 0, so we can also cross those out here. We're left then with 2xh plus h squared minus 2h all over h. A good idea at this point is to factor out an h from the numerator, leaving us with 2x plus h minus 2, and then we could see that h over h is equal to 1, so if we pull out h over h, we're left with 2x plus h minus 2. And this would be our final answer here. All right, moving on, we're looking at inverses now. We want to find the inverse of f of x equals x over 1 minus 3x. We have, I think, just a couple problems left to go here, so we're getting near the end. To find the inverse here, the first thing I would do is I would rename f of x as y. And once f of x is renamed as y, I'm going to swap my x's and y's. So now I have x equals y over 1 minus 3y. And now we're going to solve for x. So to solve for x, my next step I think of is get rid of that fraction. And so to get rid of the fraction, I'm going to multiply both sides by 1 minus 3y. The right-hand side, I'd just be left with a y there. And then after getting rid of the fraction, I get rid of the parentheses by distributing this x through. So on the left-hand side, we now have x minus 3xy. On the right-hand side, we still have y. So if we're solving for y, we want to isolate all the terms with y in them to one side of the equation. Usually I'd go with the left side, but I think it looks a little cleaner here to move everything over to the right side. So I want to get all my terms with y on one side, which means that we're going to have 3xy plus y on the right-hand side, x on the left-hand side. And then on the right-hand side, I don't want to backtrack. I want to remember I'm solving for y, so I'm going to factor out a y. Factoring out y from each of these terms is like dividing each term by y. So we're left with 3x plus 1. And now finally, I'm solving for y, so I'm going to divide both sides by 3x plus 1. And we end up with y equals x over 3x plus 1, which, because we're finding the inverse, I'm going to give that the name of the inverse. F inverse of x equals x over 3x plus 1. And we're done. Okay, the next problem that we're going to do actually uses this result, though. So we found f inverse of x equals x over 3x plus 1. And I'm going to write that down here before we go any further. So in this next problem, we're asked to find the domain and range of f of x. So we need the fact that f inverse of x equals x over 3x plus 1. Okay, so here we're asked to find the domain and range of f of x equals x over 1 minus 3x, the same function from the previous problem. So before I go any further, I'm going to find the domain of f of x. So the domain of f of x, actually I'm just going to write what x could not be equal to. We want to make sure 1 minus 3x is not equal to 0. And so that means that 1 is not equal to 3x, or that 1/3 is not equal to x. X cannot be equal to 1/3. Okay, so that's what I get for the domain of f of x. For the domain of g of x, or the domain of f inverse of x, looks a little bit similar, but it's different. The domain of f inverse of x is we want to make sure that 3x plus 1 is not equal to 0. If we subtract 1 from each side, we get 3x is not equal to negative 1. Divide through by 3, we get x is not equal to negative 1/3. Okay, similar but different, right? Okay, so to find the domain of f of x, in fact, I'm going to make you a little chart here that sometimes helps. Let's put f of x and f inverse of x here in our chart. And for each of these functions, we'll find the domain and the range. Okay, so first of all, the domain of f of x, and I'm just going to leave this without interval notation. X cannot be equal to 1/3. The domain of f inverse of x, x cannot be equal to negative 1/3. It's really easy to find the range. What we're asked to find is the domain and range of f of x. Well, to find the range of f of x, that comes from the domain of f inverse of x. We just want to make sure that we change that x to a y. So the range of f of x is that y cannot be equal to negative 1/3. It includes all values of y except negative 1/3. And then if we want to just go one step further and we want to find the range of f inverse of x, we would use the domain of f of x for that, but change our x's to y so that we have y is not equal to 1/3. Okay, so that, I believe, concludes our PowerPoint here for today. So if you have additional questions on anything, make sure that you send me a message through the inbox and or through the class email, and I'll get back to you as soon as I can. Okay, well, happy studying, and I hope you do well on the exam that covers Chapter 1.